let's begin. And first of all, I'm really happy to be here at Kotlin Conf with all of you. It's the first offsite event for me after the pandemic, and it's really cool that we meet offline. And for the next 45 minutes, we are going to talk a lot about concurrent programming. Not only in Kotlin, but about concurrency in general. First of all, a couple of words about myself. So I work at JetBrains on Kotlin Coroutines, and I'm a researcher in the field of concurrent algorithms. And for the last couple of years, I've been focusing on improving the internal synchronization and communication primitives, such as mutexes, semaphores, channels, and so on. And also, I've been teaching concurrent programming at different universities for over 5 years. And today, I would like to share some knowledge with you. And if you ask me, Nikita, how would you design some new algorithm? I would say that, first of all, you need to read a lot of books. Some of them are here on the slide. And when you read these books, you need not only to understand them, you need to implement the basic algorithms, you need to feel how to program concurrency. And reading these books is not enough. You also need to check the modern algorithms published at top-tier conferences. You need to understand them. And after that, when you have expertise, when you have intuition, then you can create something new. But it sounds kind of outdated, isn't it? Nowadays, we have a smart guy that knows all these books, all these algorithms. So we can simply ask this smart guy, ChatGPT, to implement an algorithm for us. Or we can't. Let's give it a try. Let's try to build some algorithm that is not very trivial, but still can be implemented on top of some standard collections. Let's, for example, build a concurrent bounded queue. It's like a typical queue, but of fixed capacity. So this queue can't contain more elements than the specific capacity. And when you try to insert an element, when we invoke add function, if the number of elements is already equals to the capacity, so the queue is full, then this addition fails and returns false. And the poll operation extracts the first element as it works in a normal queue. So if the queue is empty, it returns null. Otherwise, the first element is extracted. OK? So let's now try to use ChatGPT to build a concurrent bounded queue. So now I asked for you to build this algorithm. And we are here at Kotlin Conf, so the code should be Kotlin. And that's what it suggests. The data structure itself stores the capacity of the queue, obviously, and also reuses the standard concurrent linked queue from the Java library. So it's a standard queue implementation in Java. And if you program on Kotlin on JVM, then you can also use this data structure. And to maintain the size, to check whether the queue is full or not, ChatGPT suggests to use an atomic counter. So when we add a new item, we first of all check that the capacity is not exceeds. And if the queue is full, then the operation immediately returns false without doing anything. Otherwise, there is some space in the queue, so the algorithm adds this element and increments the size. OK? And the poll operation. To extract the first element, we first go to the underlying queue, trying to extract it. And if the queue is empty, we return immediately. And if an element was extracted, we also decrement the size counter. and we increment and decrement it atomically as we use atomic integer. So it looks very straightforward. It looks correct. But is it? Oh yes, I don't know. We need to check that, right? We need to check. And if you have some implementation in your code, you need to write tests. And if you go to popular concurrent libraries, if you go to the tests, you will see that these tests are very complicated. So they contain a lot of boilerplate code that starts threads manually, trying to do some work. But then we need to verify that everything is going fine. And it's really hard to verify that everything is going fine. For example, a typical test for the queue, for concurrent queue, you start 2 threads, and you transfer a bunch of elements from one thread to another. And after that, you check that all the elements have been transferred and that they have been transferred in the right order. But it's an easy to verify scenario, right? If you want to check that the capacity of the queue never exceeds, for example, under some concurrent environment, then it's hard to write such a test. And okay, let's say that we are good with this test quality. So we have a test and it fails. What are you gonna do with that? So you have an error, you know that your data structure works incorrectly, but then you need to understand the root cause of this incorrectness. And for that, you usually go to your code and read it over and over and over until you understand the bug. And it can take not hours, but days, sometimes weeks. And it would be great to have some tool that helps you not only to write robust tests for concurrent data structures, but a tool that will help you to understand, to analyze the error. Let's try to imagine that we have such a tool. Let's try to create it. So, for example, we want to write a test for our bounded queue written by ChatGPT. What I would do is that creating an initial state of the data structure, saying that, okay, we want to test this queue of capacity 2, and we have 2 operations. We have add and poll that can be invoked concurrently on the queue. And after that, it would be really nice to just run some magic button. You agree, right? So we run some magic button, and it checks that our data, whether our data structure is correct or not. And that's exactly the framework we have at JetBrains for testing all internal primitives in Kotlin Coroutines. And this framework is called Linchek. The only difference is that instead of this run concurrent test, we can specify some options to configure the test. By model checking options, we mean that Linchek should use model checking mode. I will explain later what it means. But this is the test we can write with a Linchek. And if we run this test, then we see that this test fails. So there are some incorrect results. And we are not going to analyze the error right now, because the right question at this moment would be, what is correctness in the world of concurrency? Which data structures we consider correct and which are not? And if we live in the sequential world, then the answer is pretty obvious. So for example, is this execution correct? Who thinks that it's correct? In the sequential world, this execution. So almost everybody. Who disagree? A couple of guys disagree. That's fine, but it's correct. It's correct because here we have bounded queue of capacity 2. So we add the first two elements successfully, and the following addition fails because the queue is already full. So add returns false. And after that, when we invoke poll, it extracts the first element. So it extracts 1. So this execution is correct, and it's very intuitive if we live in the sequential world. And this one is obviously incorrect because here the last addition, it must fail as the queue is already full. So it can't return true. So we know that this behavior is incorrect. So let's now run this operation concurrently. And when we run them concurrently, when we analyze behavior of our algorithms under concurrent environment, when we say that our data structure is correct, we usually mean linearizability. It's the most basic correctness property. And in brief, linearizability guarantees us that this execution we obtained, that we can express it with some sequential history, which doesn't violate the program order, which doesn't violate the synchronization, and produces the same results. Sounds complicated, but let's take a look at a couple of examples. For example, this one. So here we have bounded queue of capacity 2 and 2 threads. In the first thread, we add A and then extract A. In the second thread, we add B and extract B. Is this execution correct? Who thinks that it's correct? Is it linearizable? Can we find some sequential history that explains these results? Yes, we can. We can find such a history. We can say that first we added A and extracted A. After that, the execution switched back, sorry, not back, just to the second thread. And we added B and extracted B. So we explained the results with some sequential execution. Okay, let's take a look at another example. Now, in the first thread, we add A but extract B. And in the second thread, we add B but extract A. Is this one linearizable? So many of you say that it's linearizable, and you are right. Because we can find some history. We can say that the execution started with the first thread. So we added A. Then we go to the second one. We add B. Then extract the first element that was A. And then we extract B in the first thread. So we still can find some sequential history. All right. Another example. So here we have in the first thread addition of A and we extract B. And in the second thread, we now add B and C and then extract A. I'll give you 5-10 seconds to analyze this execution and try to understand whether it's correct or not. So, who thinks that this execution is correct? And who disagree? Okay, 50-50. All right, it's still correct because we still can find some history. We can start from the second thread. So we first add B. And after that, we switch to the first thread. So we add A and extract the first element that was B. Now the queue contains only A. Then we go back to the second thread and we add C and extract A. So we can provide a sequential history that doesn't violate the program order, which means that our execution is linearizable. So it's correct. Okay, the last one. The difference between the previous one is that the poll invocation in the second thread returns now C. So 5-10 seconds again. Think about it, whether it's correct or not. It's not so obvious. Okay, it's not possible. You're right, it's impossible. And why is it impossible? Because for all these additions to return true, we need the following prefix. We need to start from the second thread. We need to add B, then switch to the first one, execute it, and switch back to the second thread. And if we do so, then poll can't return C. It must return A, right? And any other history would result in one of the additions to return false. So we can't find a sequential history that explains these results. And it means that this execution is incorrect, is not linearizable. And when we say that our data structure is thread safe, is correct, is atomic, we mean that it's linearizable, so that all possible executions are linearizable. All right. And let's now switch back to our bounded queue, to our test. And here we see that we have two threads, we have only additions here, no polls, and all these additions return true. But we have bounded queue of capacity 2, and we added 3 elements. We can't express these results with some sequential history, because one of these additions must fail. But it doesn't. So this is incorrect. And what is more importantly, that Linchek not only shows you a counterexample, it also provides you a comprehensive interleaving trace that explains the error. So here we see that here is a trace. Now we're going to analyze it. And for that, I've put the add implementation on the slide and the data structure state. Now the queue is empty, the underlying queue, and the size is 0. Now we'll see why this bounded queue is incorrect. So we start with the second thread, and first of all, we check whether the queue is already full or not. So we read the size counter. The size is 0, so the queue is not full, and the algorithm goes to the next step and adds the element to the underlying queue. And now the underlying queue contains 6, but the size count is still 0. And the second thread gets preempted, so the execution switches to the first one before incrementing the size. And now when we switch to the first thread, we add 2. So the size was 0, now it's 1. And the underlying queue contains now 6 and 2. And the following addition also succeeds, as the size was 1. So this addition, it thinks that the queue is not full yet. So it adds a third element into the underlying queue. And when the execution switches back to the second thread, it increments the size counter. And now we see that the queue contains 3 elements, and the size counter also equals 3. So this addition also succeeds. And the problem here is that we incremented the size and add an element to the underlying queue non-atomically. So we can, like here, preempt the operation in the middle which leads to a bug. I will not show how to fix this error, but what I want you to show is that with Linchek, it's really easy to analyze concurrent errors. So you not only have a robust test, you also have a great tool which helps you to debug your algorithm. And now let's deep into how Linchek works. First of all, Linchek generates a lot of different random scenarios, putting the specific operations into multiple threads, like here, and then it examines these scenarios either via stress testing. In this case, Linchek fairly runs multiple threads and invokes the scenario multiple times in hope to get in a bad situation and detect a bug. Or it can also run the scenario in model checking mode. In this case, Linchek controls the execution. So it decides where the thread should be preempted, and that's how we obtain these nice interleaving traces. Since Linchek controls the execution, it knows how to reproduce the bug. So it can tell us, hey, here is the trace. You can use it to understand what's going on. And finally, after we executed our code, we have some results which we need to verify. And the last stage is the verification stage. So Linchek tries, for each result, it tries to find a sequential history that explains them, exactly as we did on our examples, but Linchek automizes all the process. Okay, so it generates random scenarios, runs them, and checks the results. So it generates scenarios automatically, checks results automatically, runs them automatically. You just need to tell Linchek what you want to test, not how to test, just what you want. And let's also try to understand how we get these traces, because it's non-trivial, right? We have such a trace, but we didn't insert, we didn't use specific primitives so that Linchek can control the execution. And what Linchek does is that it transforms bytecode on the fly. And I would like to use a simple example now to show you how the bytecode transformation works. For example, we have such a counter with the only increment and get operation. And the implementation is that we increment the counter non-atomically, and then we read it again to return the new value. So this implementation is correct in the sequential world, but it doesn't look correct under concurrent updates. Okay, let's take a look how compiler transforms this Kotlin code into JVM bytecode. After the compilation, we have the following code. So we first read the counter value, we increment it locally, and then we write a new value via the put field instruction. And finally, we read the value again. So here are three atomic, three instructions that manipulate the value field. And Linchek transforms this bytecode, adding adding internal method invocations before these instructions. So before get field, it adds Linchek before read method, before write, it adds before write, and so on. And Linchek supports not only get field and put field instructions, it supports all the ways to manipulate shared memory. So if you use atomics, if you use unsafe, var handles, atomic field updaters, if you use synchronized blocks, and whatever else you can use, Linchek supports all these synchronization constructs. So that's how it works. And if we write a Linchek test for the counter, take a look at its 6 lines of code. Sorry, 7 lines of code. This test will fail with the following error. So it provides an interleaving that explains the error. And what actually is going beyond the analysis is that Linchek added this before write function calls that decide whether we continue the execution or we switch to another thread. And here we see that we start from the second thread. We read the current counter value, and Linchek decides that, okay, we should read it, so we don't switch. After that, before updating the value, Linchek decided to switch. So we switch to the first thread, we complete it, and after that we switch back to the second thread, and we ask again before read whether we want to switch somewhere or continue, and Linchek decides to continue, and here is the trace. That's how Linchek obtains such traces, and it internally studies many different interleavings by changing these decisions, whether to switch or not. All right. And here's the question related to the talk title. How we test concurrent algorithms in Kotlin Coroutines? Yes, we test them with Linchek, and we've been using Linchek for a while. And the first time we started using it, we found many bugs. Here are some of them. They're already fixed, so don't worry. Everything works fine. But I want to highlight that we had very nice stress tests, plenty of them, and we still were able to find new bugs. And we used Linchek not only in Kotlin Coroutines, we used it in some other libraries. For example, we used it to find bugs in GCStress. I think many of you have heard of GCStress. It's a very famous library with the concurrent primitives. And we also managed to find a bug even in the standard Java library. So you can try to write a Linchek test for concurrent linked DAC data structure. And in the very recent Java version, you will find an error. So it still doesn't work. And the funny story is that it never worked. They tried to fix it a couple of times, but we are still here. They just need to use Linchek. Actually, they don't use it. And it's interesting, but it's still not very important. The key feature of Linchek is that it can provide the interleaving trace, so we can easily analyze the error and understand the bug. And for the last couple of years, I've been working on new channel algorithms for Kotlin Coroutines. So we improved the implementation significantly. And it was impossible to do that without Linchek. You remember, if you have a stress test and your test fails, the only way to analyze the error is to read the code over and over until you understand the bug. Here is a part of the algorithm. No chance to understand this if you just read the code. But if you have a proper tooling, if you have a robust test that can explain what's going wrong, in this case, we can do that. We can understand all the issues, and it takes much less time. And without Linchek, it was impossible. That's why we actually added the model checking mode. Not because it works better than stress testing, no, but because it changes the process of writing new algorithms. So you can check your hypothesis fast. You can just write it, implement it, and run the test. And in a couple of minutes, you know whether your idea is correct or not. That's how it works. And to summarize here, please never, never, never use ChatGPT to implement not only concurrent algorithms, to implement anything that requires thinking. Because ChatGPT knows a lot, but unfortunately it can't think at the current moment. And if you write concurrent code, please use Linchek. It's very easy. It will take 5 minutes at most for you to start using it, but you will like it. You will be sure that your data structures are correct, so you will sleep well. And at JetBrains, we are now working hard on making Linchek better. We are working on various new features, so stay tuned and track the updates. And now we have 10 minutes for the questions. So thank you all for coming.
Hi. Great talk, by the way. Quick question. How did Linchek know that the increment and get case was wrong? I mean, obviously we know that it's wrong, but how does it compare to a non-concurrent version, or how do we know that that both results are one, that is incorrect? If you understand the question.
I got the question. Thank you. It's a very good question. And here we see that when we write an Linchek test, we don't explain how increment and get should work. We just run the test and some magic happens. But there is no magic. Remember, when we talked about correctness, in concurrent world, we used linearizability. And we say that an execution is linearizable when we can explain it with some sequential history. So what Linchek does is that it tries to find such a history, and to produce the results of these sequential histories, it uses this implementation you provided. So it runs the same code, but sequentially, assuming that it's correct in sequential world. In Linchek, we also allow to specify sequential implementation, a separate one, so you can be 100% sure that you didn't do a stupid mistake, but it's not necessary. So because we check not the counter, we don't need to understand the semantics. We just need to find a sequential execution because we check for linearizability.
Here was a question.
Thank you. Thank you, really nice talk. Do you still have the cases with Linchek that it reports a failure only occasionally because the test is flaky for some reason? Like maybe there is some really weird specific scenario where it fails only like every other run or something like that.
You can have a flaky test, that's true, because if you examine scenarios in stress testing mode, so on some hardware you can obtain incorrect results, on some hardware you don't. What you usually do is that when you obtain some incorrect results, you can tune Linchek, you can tell it to make more invocations. So now you are sure that it will more likely fail. But it's still testing tool. So if you use Linchek, if you use Linchek, you are almost sure that your data structure is correct. But you should understand that Linchek generates different scenarios. And maybe it haven't generated a scenario which causes the bug. So it generates many scenarios. So it will likely generate one, but it's not guaranteed. That's why, for example, in Kotlin, when we worked on new mutex and semaphore algorithms, we also proved them formally. Because they are tricky, and we tested the implementation, but we also wanted to be 100% sure that our ideas are correct. So, yes, answering your question, it's Linchek test can flag, but it's fine because any test can flag. And you should understand that Linchek doesn't prove it tests your data structure, but it does that very well.
Can Linchek look for concurrency properties other than linearizability, other consistency models and things like that?
Yes, Linchek supports some eligibility relaxations. We now have support for quiescent consistency, if you're familiar with it. We add code for other correctness properties for some relaxations, but since we don't know real use cases, we don't have them released. But if you have one, please create an issue, and we'll be happy to add these properties.
Thank you for the talk. My question is about constraints on the data structure, like counter on this example. So here it returns int, and like in sequential, like check, we know like it should return 1, 2, and so on. Let's say if it's a service and it has side effects, can I still use Linchek, for example, like setting up what are expected side effects or something like that? Does my question make sense?
It makes sense, but I would say that Linchek is not a silver bullet. So it was designed to test data structures. So the idea is that it not only provides you automatic stress testing and model checking, it also generates scenarios and also automatically verifies the obtained results. That's the idea. And in your case, when you have some concurrent code and you want to check for specific properties, maybe it's better to write a stress test. Because with Linchek, if your code has side effects, I'm not sure that it's good to use Linchek.
You mentioned, are there useful concurrent data structures which are not linearizable, which would produce false positives in this scenario, or are pretty much all known useful concurrent data structures ones that are going to satisfy the properties that this is checking?
That's a very good question. Are there useful data structures that are not linearizable? We have such a data structure in Kotlin Coroutines scheduler. We have a queue which is not linearizable but is quite inconsistent. So it's kind of a linearizability relaxation which allows some reorderings. And we use Linchek to test it. But there are many data structures that are not linearizable. For example, if you want to have a very, very scalable queue, very scalable priority queue, you can use the multi-queue approach. It's an approach where you have a bunch of sequential queues protected by logs, and you add an element to a random one. But when you need to extract an element, you check 2 queues and you extract the best element. And surprisingly, this approach is pretty fair. So if you're fine with the reorderings, if you don't need strict ordering, then you may use this approach, but unfortunately you can't use Linchek to test it because this algorithm is probabilistic. But okay, you can use Linchek to test it if you always put, if you always insert the same values, so you can test it as a bag, not as a queue, and that's what we do in some research projects. But this is the data structure, which is definitely not linearizable, but very useful.
You mentioned that you generate inputs a la Foster. Fosters normally use code covers to kind of guide whether you're generating good inputs. Do you use something similar?
Right now, we don't use code coverage, but it's on our list. So I think at some point we'll add this heuristic.
Is it possible to replay your fast or your generated scenario to test again if your new implementation works with the new scenario or with the previous scenario?
Right now, you can run the test again, and Linchek deterministically generates scenarios. So it's very handy because if you have a Linchek test failed, I don't know, on Team City, for example, and you want to reproduce this error on your local machine, you run the same test, and it will also fail. But I will open some cards. Right now, we are working on a plugin for IntelliJ IDEA, which will allow you to analyze these interleaving traces, such as this one, in debug mode. So you are able to step forward and backward and see how your data structure changes. But it's not released yet. I hope that we'll finish the work soon, and so stay tuned. Hope I answered the question.
A short one.
What are the best practices? When should we use stress tests, and when should we use like model-based tests?
That's a pretty good question. So the question is when we need to use stress testing and when we need to use model checking. And the current model checker in Linchek, it assumes the sequentially consistent memory model. It means that if you forget to insert volatile, then no bug will be found. Because no weak memory model facts are covered with the current model checker implementation. So if you want to be sure that your data structure is correct under weak memory models, so please use stress tests as well. We usually run both model checking and stress tests, kind of spending more time on model checking as it is slower, but we run both. And the model check, even if it supports relaxed, even if it supports weak memory models, it can have bugs, right? So it's software. We all produce bugs. So I personally, even in this case, would use stress tests just to sleep well. Thank you.